Hi, it's Mrs. Gregg. Today we're looking at the atom in a little more detail. We'll look at its structure, we'll look at the atomic number, and we'll figure out what we mean by isotopes. Let's review the subatomic particles that we've learned so far. We have the electron, the proton, and the neutron. And you can't forget who's responsible for discovering each of these particles. We have Thomson, who had the plum pudding model, Rutherford with his gold foil experiment where he discovered the nucleus, and then subsequently discovered the proton, and then we have Chadwick responsible for the neutron. We have a table down here that lists out the subatomic particles and compares them. I'm concerned today with the relative electric charge and also with the relative mass. So an electron we know carries a -1 charge, a proton a +1 charge, and then a neutron is neutral with no charge. And then as far as the mass, protons and neutrons have approximately the same mass, but an electron is significantly smaller, has a lot less mass than a proton or a neutron. Let's look at what we mean by atomic number. So there was an English scientist who discovered this relationship that if you look at the atoms of a particular element, that they're always going to have a unique positive charge in their nucleus. And so what he discovered was that what identifies particular elements is that positive charge, which equates to the number of protons that are in the nucleus. So we have this number, the atomic number, and it identifies each atom of an element. It identifies each element according to the number of protons that are in an atom of that element. So let's look at an example. We have down here hydrogen, helium, and lithium. So hydrogen has 1 proton. It would have a +1 charge on its nucleus, and so its atomic number is 1. If we look at helium, helium has 2 protons in its nucleus, so its nucleus carries a +2 charge. Its atomic number is 2. And then lithium has 3 protons, has a +3 charge on its nucleus. Its atomic number is 3. Okay, also with atomic number, as you look at the periodic table, the way you figure out the atomic number of an element is by this number here at the top. Okay, so we have beryllium here, which is the 4th. We just looked at the first 3 atomic numbers. We're on to the 4th here with beryllium. Its atomic number is 4. And what that means is that there are 4 protons. We can count them here in the nucleus. And it just so happens, since atoms are neutral, if there are 4 protons, if there's a +4 charge on the nucleus, then that means that there must be 4 electrons out here to balance out that +4 charge. So that means we have 4 electrons orbiting. So from the atomic number, we can figure out the number of protons and the number of electrons in a particular atom just by looking at this atomic number here. Okay, the periodic table. How are we going to read this? We've got this hanging up on the wall. What do we do with it? There are certain trends in it. For one, as you go across the periodic table, if you pick a particular row, we call that a period, and the atoms, the elements increase in atomic number as you go across this period. They'll also have similar physical properties. So if you picked everything here in this particular row, they would have similar physical properties. For instance, like boiling point or melting point or how well they conduct electricity. There would be trends there that we could see in that row, and we call that a period. Now going vertically, we have a group. Elements that are in the same group react with other elements in similar ways. And we'll look more at the periodic table in detail in the next unit, but just so you have a general idea. All right, and then it's arranged according to atomic number. So atomic number 1, here we have hydrogen, we go across, 2 is helium, 3 lithium, 4 beryllium, and so forth. So it's arranged in order of increasing atomic number. And again, the way you figure out the atomic number, that's the one we see on top of the element symbol. And then beneath the element symbol, we have the atomic mass that we'll talk about in just a second. All right, so isotopes. If we think back to Dalton, and remember he had this billiard ball model of the atom, there were limitations to his model. For one, he said that atoms are indivisible. We know they aren't because we have these subatomic particles. He also said that all atoms of an element are identical. Well, they aren't identical either, and that's where these isotopes come into play. Okay, so the way you identify a particular atom of a particular element is by its number of protons. So for instance, hydrogen is always going to have 1 proton. It's always going to have that atomic number of 1. If you go to helium, it's always going to have 2 protons. It's always going to have that atomic number of 2. But as you progress through these different atomic numbers and you start comparing the number of neutrons that are in the nucleus of these atoms, the number of neutrons can differ. It's not always going to be the same number of neutrons whenever you examine an atom. So isotopes are going to be atoms with the same number of protons, because it's the number of protons that identify what element it is, but now they can have different numbers of neutrons. So let's look at an example. Okay, let's take potassium. Potassium, there are 3 different isotopes of potassium. Okay, so they all have 19 protons. That's what makes it potassium. But if we look at the number of neutrons can differ. So we have one that's identified as potassium 39 that has 20 neutrons. Potassium 40 has 21 neutrons, and potassium 41 has 22 neutrons. Now, the way we get this number is by adding together the number of protons and neutrons. And that's how we identify the different isotopes. All right, and then also notice that the electrons stay the same, because if we are going to have a neutral charge, then the number of electrons and protons have to balance out. So again, with the atomic number, that's the number of protons. It also tells you the number of electrons. And it's the atomic number or the number of protons that identifies what element we're talking about. So 19 all the way across here for everything, we know we're talking about potassium. But what differs is the number of neutrons. We have 20 in this particular atom, 21 here, and 22 here. Isotopes are written according to what we call standard atomic notation. So what I mean by that is we have the element. So potassium is abbreviated with a K. We have the element. We have the mass number. We'll look at what the mass number means in just a second. That comes right here in the upper left. And then we have the atomic number, that number of protons. And like we said, potassium has 3 isotopes, and this is how we denote those 3 isotopes. And where you see the change is in the mass number, which identifies the fact that there are differing numbers of neutrons in that nucleus. Number of protons always stays the same, it's always 19, but there can be different numbers of neutrons. And so all 3 of these are different isotopes of potassium. Okay, here's that standard atomic notation again. You have the element symbol, and then you have the mass number in the upper left. The mass number is the sum of the protons and the neutrons. And then we have the atomic number that we talked about before. On the periodic table, you find that atomic number up above the element symbol, but here with the standard atomic notation, the atomic number is going to show down in the lower left, and that's going to tell us the number of protons. So let's compare 3 different isotopes of hydrogen. So we have hydrogen 1, that's the hydrogen that you're most familiar with, and it has 1 proton, it has no neutrons. Its atomic mass is the sum of the neutrons and the protons, so its mass is 1. We have another isotope of hydrogen that we call heavy hydrogen because it has an extra neutron. So whenever we add the neutron plus the proton, we get an atomic mass of 2. That mass is indicated here. 2, that's the protons plus the neutrons, and 1 is the number of protons. And then there is a third isotope of hydrogen that's even less common than this one is. And that one, the atomic mass is 3. We know that the number of protons is always 1 because that's what identifies as being hydrogen. So that means 3 minus 1, the mass number minus the number of protons, tells us that there must be 2 neutrons in the nucleus of this hydrogen atom. Let's talk about how frequently you find certain isotopes in nature. So in nature, elements are found not as one single isotope, but as mixtures of isotopes. And there is a certain relative abundance, there's a certain percentage of each type of isotope that you'll find in nature. So let's look at potassium as an example. So if we take a banana, bananas are full of potassium, good for you. If you take a banana and we look at that potassium, 93.26% of that potassium is going to be potassium 39. A very small fraction, this 0.01% of potassium is potassium 40. And then 6.73% of the potassium is going to be potassium 41. So we have a mixture of all 3 different isotopes that form the potassium that would be in this banana. But now if you took a sample of potassium from somewhere else on Earth, say you went out in your yard, you dug up a sample of Earth and figured out what potassium was in there, or if you looked at a plant or any other place where you might find potassium, you're going to find that same relative abundance. You're going to find these same percentage profiles of isotopes for that potassium that you're looking at. So that's what we call the relative abundance of isotopes. All right, now let's look at the mass of atoms. We talked about the fact that a proton and a neutron have approximately the same mass, and we're showing that here. And then an electron is significantly smaller compared to protons and neutrons. It has a very teeny tiny mass. Okay, because these masses are so small, and at the first table that we looked at on the very first or second slide, it listed out the exact mass in grams, and it was something like 10 to the minus 27 or something. That's a teeny tiny small number, and it becomes difficult to work with those small numbers. So what scientists have done to simplify things is to assign relative masses. And so the relative mass of a proton we call 1, roughly, and the relative mass of a neutron we call 1, roughly, and then the relative mass of an electron is significantly smaller, but not in that 10 to the minus 27 range. All right, so we call these things atomic mass units. An atomic mass unit is nearly equal to the mass of a proton or of a neutron, and the definition for an atomic mass unit is an atomic mass unit is 1/12 of the mass of a carbon-12 atom. So that's our standard. But it just makes it a lot easier to discuss relative masses when we're dealing in terms of 1 versus 10 to the minus 27. All right, so a neutron is approximately 1 AMU, a proton approximately 1 AMU, and an electron teeny tiny. Let's talk a little bit more about atomic mass. When you look at the periodic table, you'll see the atomic mass of an element listed down here underneath. It's rarely a whole number. One of the reasons why is because it's a weighted average of the mass of all the different isotopes that are available for that particular element. So let's use chlorine as an example. There are 2 different isotopes for chlorine. You have chlorine-35, you have chlorine-37. The natural abundance of chlorine-35 on this earth is that 75.78% of all chlorine on earth is going to be chlorine-35. And then 24.22% of all chlorine on earth is going to be chlorine-37. If you want to figure out the average mass for chlorine, for all of the chlorine on Earth, for those atoms, then you do a weighted average, and you consider the fact that 75% of all the chlorine on Earth is going to be this chlorine-35, and the atomic mass for chlorine-35 is you're adding up the protons, the neutrons, and the electrons, and you come up with this, here, the 34.969. You come up with that for the atomic mass for chlorine-35, and so that contributes to 75.78% of all of the chlorine on Earth. And then here with chlorine-37, whenever you add up the protons, the neutrons, the electrons, and you figure out the mass, then that mass is this 36.966 atomic mass units, and that contributes to 24.22% of all the chlorine on Earth. So you do a weighted average, and you come up with an average mass for chlorine being 35.453 atomic mass units. All right, now you can use that information and kind of go backwards with it. If I told you that there are 2 isotopes of chlorine, that you have chlorine-35 and chlorine-37, and if I told you that the atomic mass of chlorine, this is the average atomic mass, the one that we see on the periodic table, is 35.453 atomic mass units, then if I asked you which isotope is most abundant, is it the 35 or the 37, by looking at this number and seeing that the chlorine-35 is closer to the actual average atomic mass, then you know that chlorine-35 contributes more of a percentage to this weighted average than does chlorine-37. So chlorine-35 is the most abundant one because it's closer to the average than the chlorine-37 is. Okay, let's finish up by looking at numbers of neutrons. All right, in small atoms, that's those at low atomic numbers, like your hydrogen and your helium and lithium and beryllium, and these, I've got some more examples up here, nitrogen, oxygen, small atomic numbers. The number of neutrons is roughly equal to the number of protons. So what I'm showing here is we have 14 is the sum of the protons, the neutrons. We know that there are 7 protons. That means that there must be 7 neutrons for nitrogen. Okay, so 7 protons, 7 neutrons were equal. With hydrogen, we know there are no neutrons, so we just have 1 proton. With oxygen, we know that there are 8 protons, and then the sum of the protons and neutrons is 16, so that leaves there must be 8 neutrons, so roughly equal again. Okay, so at low atomic numbers, the number of neutrons is roughly equal to the number of protons. Sometimes you can be off by 1 or 2. All right, but the higher you get with these larger atoms at high atomic numbers, then it becomes the fact that you have significantly more neutrons than you do protons. So I picked gold here as an example. The mass number for gold is 197. The atomic number is 79. So we know that there are 79 protons, but if you subtract the 79 from 197, you get what, like 118 or something, which is not nearly equal to the 79 down here. So we have a whole lot more neutrons than we do protons in gold. As we get to these higher atomic numbers, that becomes the case. You have a lot more neutrons than you do protons. Okay, so now we ask why. Remember that protons all carry a positive charge, and so all of this positive charge lumped together in that nucleus, the protons tend to repel each other because the positives are repelling the positives. Remember, it's opposite charges that attract, but like charges are going to repel each other. So we have all of these protons that have this tendency to repel each other. The neutrons are actually like a binding, almost like the glue that holds the nucleus together. The neutrons are attracted to protons and help to bind the entire nucleus together because of something called the residual strong force. And it just says that whenever you have 2 particles that are very, very, very close together, that they tend to be attracted to each other, and that attraction is stronger than any repelling force that you would have from the protons. Okay, so it's this residual strong force which is the neutrons in with the protons that helps to bind everything together and keeps the protons from just flying apart and the nucleus flying apart. So neutrons are like the glue that holds it together. As the nucleus gets bigger, whenever you start lumping in bunches and bunches and bunches of protons, then this repulsive force from all of the protons, this tendency for them to repel each other, becomes even greater. It's almost like an exponential growth. It becomes even greater because you have so many protons. So in order to compensate for this increased repulsive forces of the protons wanting to come apart, we have to have more neutrons. It's like more glue, more residual strong force to overcome that repulsive force of the protons to hold that nucleus together. So just in a nutshell, at these higher atomic numbers, you have not equal numbers of neutrons, but you have a whole lot more neutrons in order to keep the nucleus together as one single cohesive thing. Okay, but at lower atomic numbers, in general, the number of neutrons equals the number of protons. All right, and that is it, and I will see you in class.